Boom. The only force acting during flight. So arrows, rocks, people sometimes, if you throw a person, kick them off a building, I don't know. All projectiles. Gravity is the only thing acting on these things during the flying. So Kai, you're almost all the way there. There is an initial burst, and then there's nothing. But there are also things that we give an initial burst to that would not be considered projectiles. Things like frisbees. Frisbees are not projectiles. Why is a frisbee not a projectile? What else is acting on something like a frisbee after you huck it? We've played with frisbees before, yes? Okay. Well, frisbees are designed to do what? Yeah, right now.
Is it because frisbees ignore air resistance?
No, nothing ignores air resistance. There is something that frisbees are designed with in a particular concept in mind so that they don't just fall due to gravity. Frisbees are designed to do what? Or I'll give it another, let's go talk about planes. If you take the engine off a plane, what do you have? Like, what is that object now? Without an engine, a plane is starts with a G. Kale, what were you saying? A glider. A plane is a glider. So a glider, whether it's like a hang glider or it's one of those big white gliders, a little cockpit, you drag it up into the air with a plane and then you cut it loose. Those things are designed so that what, in addition to gravity, acts on them? 4 letters, starts with an L. Okay? How does a plane stay up? There's lift. The wings are designed so that it has lift. Whether it's a glider or a frisbee, they're designed such that there are other forces that are going to keep that object up in the air should you cut the engine or if it never had an engine to begin with. So anything that's designed inherently to have lift cannot be considered a projectile. Those things get more complicated. Anything that doesn't have lift inherently, a human being, for example. There is nothing aerodynamic about my 4-year-old. Trust me, I've tried. Again, like I say, one of her favorite games is to run across the living room, get thrown back across the living room into the couch. There is nothing aerodynamic about a 4-year-old. Arrows, again, arrows don't inherently have lift either. You don't have little wings on them. There's feathers on the back, but those aren't to keep the thing up. The feathers on the back are to keep it stable. So an object traveling through the air where gravity is the only force acting during flight is what we call projectiles. Missiles are out. Frisbees are out. Gliders are out. So there's a whole bunch of different things here that we have to ignore. So projectiles can look like any of these things. I'll draw a few. If you take an object and you drop it. If you drop the thing, the initial velocity is 0. VI equals 0. And the only thing acting on this thing is gravity, causing it to accelerate downwards at negative 9.8 meters per second squared. That's it. If I take an object, instead of dropping it, I throw it down. I mean, now I've got a non-zero VI. VI is not equal to 0. But again, the only thing acting on this thing is an acceleration due to gravity downwards. And we've looked at both of these already. The quiz I gave you yesterday had this scenario. You're taking the gondola between Whistler and Blackcomb and the cable snaps. How fast are you going to hit the ground? Some of you told me that you're going to hit the ground at 0. I can assure you, you won't. You're going to hit the ground at a very large number, and the ground will bring you to 0. It's the act of being brought to 0 that is the problem. We've looked at this one too, if I'm not mistaken. You take the object and you throw it up. Thing's going to come back down. We've looked at those problems too. Gravity is the only thing acting there. We've looked at this problem. On top of a building, you throw the thing up, it comes back down. So at this point, and we've done these already. At this point, the only thing we haven't looked at is what happens if, these are all very specific scenarios, what happens if instead, and that's what we're going to look at today, tomorrow, and the next day, I take an object and I throw it that way. Or what happens if I take an object, and let's make it even more interesting. I take an object and I throw it that way. Or as Kai said earlier, there is one kind of big blast of energy at the beginning. The throw is the blast of energy at the beginning, and now the object just gets taken over by gravity. It's going to end up somewhere. So we're going to look at this, we're going to look at this, we're going to look at this interesting scenario. And then last of all, we're going to look at this. Where these ones, that guy there, and that guy there are the most interesting. So at its kind of infancy, these were the kind of scenarios that physics really did kind of get born. The study of physics had everything to do with these. Why do we care about these kinds of questions as a human race? What kind of use do these 4 scenarios have? Yeah, Kai. Any war. I'm over here, you're over there. I'd like you dead, and I'd like to get not close enough to you so that you can kill me back. Yes. Or I'm over here and I want to eat that animal way over there. If I get close, the animal will know I'm here. So I want to be able to get to the point where I can huck something and kill something over there without me getting involved personally. This is really where physics started. Way back. So let's look at some of these kinds of questions. We'll look at how we approach them, and then I'll leave you with something to play with. There we go. If I were to throw an object sideways and drop an identical object at the same time, what's going to happen? We've kind of done this already. Let's get some books that I don't care about and bother Mr. Keeley's class. Math Makes Sense 9. That's a terrible textbook. And Mathematics 11, also a terrible textbook. Okay, here we go. I hope I was able to successfully convince you that it did not matter what the mass of the object was when we went up to the rotunda before spring break and we dropped a bunch of stuff. We had volleyball, we had a really big book, we dropped things, we put a piece of paper on top if you recall all these things. I hope I was able to successfully convince you that the mass of the object had nothing to do with whether or no the rate at which it fell. Acceleration and gravity acts on everything. I don't think I did this part though. What happens if I throw one of these things sideways? Is that going to have any impact on these things? You're arguing it shouldn't. Why? Gravity's going to affect them both equally. Okay? Anybody have any other thoughts? Does everyone agree with Raina? And I just have to prove it a couple times. You disagree, don't you? Why? Okay? You think that somehow I'm going to be able to give the object lift? Like the lift in the book? Is that what you're talking about? Okay. Now I have to do it without hitting anyway. Where am I going to go? Let's go this way. No, I'm not going to go up, because up and over is a different scenario. What if I go like this? Let's see if I can do this. I've been practicing for a good long while. So, I mean, I have to drop them from the same height. So let's drop them from here. I'm going to drop the one on the left. I'm going to throw the one on the right. Hopefully not hit anybody. Hopefully you guys can still see. And if I do this right, let's see what happens. That was pretty good. It sounded like they hit at the same time. That one started here and ended over there, and I dropped this one straight down. And they hit at the same time. So, I mean, at least at this level, Rain was right. Gravity affected them equally, and it didn't matter that I chucked one sideways. The argument that students want to make now is what? At this point, students will say yes, but. Who has an issue with what I've just done? Yeah.
I agree with what you said, but I would say the main argument is you didn't throw it fast.
There it is. Didn't throw it fast enough. So I'm going to pull up one of my favorite TV shows of all time, Mythbusters. And I'm going to show you an example of the same kind of test done with objects that move a whole heck of a lot faster than I could possibly throw them. So, hands up if you ever watched Mythbusters, like on your own for fun. Fantastic. Not nearly enough hands. Mythbusters was an awesome show, and for those of you who are interested, I've actually found out it's on Prime. All 12 seasons or whatever are on Prime. It's fantastic. And so one of the examples that they did was exactly this scenario. I will show you the bullet drop. Okay. Where is it? Let's do this one. Okay, here we go. So this is exactly your argument. I didn't throw the book horizontally fast enough, but if we were to throw something fast enough sideways at the same time we dropped an identical object, it should be different, is your argument.
Actually, I agree. I just said that. I feel like
that would be the argument students would make.
Yeah.
Okay. So they found a warehouse. They got a handgun because a rifle would mean you just need more space. But I think a handgun is going to sufficient. I'm hoping that for any of you who did say yes, the speed at which, because that always happens. Students argue about the speed. A handgun is going to shoot the bullet at several hundred feet per second. It's going to move very, very quickly. But bullets from guns, people don't think about this. Bullets from guns drop if they don't hit anything. You shoot a gun straight up, the bullet will come back down eventually, which is problematic. The gun fired horizontally, those bullets will eventually hit the ground, assuming they don't hit something in between. And so what they've done is they've got this warehouse and they've got a handgun at one end. They have calculated based on the muzzle velocity of this handgun how far that bullet should fly before it hits the ground. But, you know, to account for error, you saw the paper he laid out was pretty big. The idea being that somewhere along that paper, that bullet should hit the ground. As soon as the bullet moving at its speed hits that paper, it will rip. So you get a very good visual representation of what's happening. And out there, you can kind of see it here in the blurriness, right here, is a drop rig. So this whole setup is designed so that At the same moment the trigger is pulled here on this gun, this apparatus is going to drop its own bullets straight down. It's just going to let go of the one that it's holding. And they should, theoretically, hit the ground at the same time, is what Reyna argued. Kai agreed with and is giving him, yeah.
Is the bullet that's being dropped, is it going to be dropped sideways?
It's a good question. Let's see if we can see it.
If it's going to be dropped down, I feel like it would drop slightly faster.
Well, there it is. Can you tell how it's sitting?
It looks like it's going down.
Looks like it's going straight down to me too. The reason you drop it straight down is to minimize drag. If you dropped it sideways, I mean, the only thing that you're doing, it would be less aerodynamic. But this isn't very tall. The thing's not moving very fast. Air resistance is a property of air resistance is how fast an object is moving. The faster it's moving, the more air resistance on the object. So this thing won't experience a ton of drag. Now let's see. Okay, so the high speed that you're going to see, for those of you who aren't aware how high-speed footage works, slows everything down to thousands of frames per second, or a frame is a very small amount of time. So the slow motion, you saw at regular speed, it looked like they hit the ground at the same time. I'm hoping you've noticed that. You're going to see the slow motion, there is going to be a slight difference, but he's going to explain how slight that difference actually is. So do pay attention to this next part. Okay, so you can see here, this one hits the ground first. But how much time was that actually? So the argument I get from students all the time is is what they've just disproven. It doesn't actually matter, assuming there's no lift, it does not matter how fast that horizontal object is going. Which leads us to quite an interesting result. Let's take a look at it. If we were to throw the thing at this horizontally, oops, don't want that. It doesn't actually change anything. Why? Let's do the math behind all of this. Okay, so we've got an object. We're going to take our object, we're going to boot it sideways, we're going to take an identical object, and we're going to drop it. That doesn't look identical. Let's say that looks a little bit more identical. We're going to give this thing some initial horizontal velocity. So we'll call this guy Vix, an initial velocity in the x direction. This guy is going to get a VI of 0 in every direction, and this one's going to be dropped. We've looked at this a bunch of times. It was in the quiz I gave you yesterday. For something like this, the initial velocity is 0. It's going to have an acceleration due to gravity, negative 9.8 meters per second squared. We don't know what the final velocity is, but it is going to have one. It will be non-zero. And we don't know how much time it's going to take, but eventually this thing's going to hit the ground. The time it takes is going to be determined by what? The distance dropped. So let's call this d. These guys are getting dropped from the same height. Whatever that distance is, let's just call it d. That's going to determine how this guy falls. This guy, I'm hoping I've convinced you based on the one demo I just did in the Mythbusters footage I showed you. This guy can be broken up into two portions. Because it doesn't actually matter how fast the thing's moving sideways, we can break them up and say, okay, well, there's actually an x portion and a y portion here. Or to put it differently, a horizontal version and a vertical version of this problem, or portion of this problem. For this guy, does this guy have any vertical velocity given to it at the beginning? No. So now I'm going to say that this VIY is equal to 0. There's no vertical velocity given. It's just the horizontal velocity. We kick the thing sideways. Gravity, as Raina said, acts on this one the same way it acts on this one. So this now is going to be given an acceleration in the y direction of negative 9.8 meters per second squared. It's going to fall a particular distance. I'll call this dy equals d. I don't know what the final velocity in the y direction is going to be. And I don't know how long it's going to take to fall. But that's all of the information that we've looked at in this whole unit. Initial velocity, final velocity, displacement, acceleration, and time. So, what's going to determine this time? The time it takes to fall. Well, it's exactly the same setup as this one here. So the thing that will determine how long it takes to fall is the same as it did here. It's just the vertical distance is dropping. So these two times are going to be equal. Let's take a look at the horizontal portion of this. The horizontal portion says, okay, I've got a VI in the x direction of some non-zero value. Let's call this VIX. Or we'll call it VI. It's been given some value. Is the thing accelerating in the x direction? After it's been kicked and it's already moving, is it going to accelerate? Or think of the bullet from the gun. Did the horizontal velocity of the bullet change at all while the bullet was flying through the air? No. So AX is going to be 0. The horizontal velocity for that object doesn't change. If we ignore air resistance, or we can treat it as being minor, there is no acceleration left and right. If there is no acceleration, what is the V final velocity in the x direction? An object's not accelerating. Its final velocity is going to be related to the initial velocity. How? Yes, Yuli, louder. It's going to be the same. So then how do I figure out how far the thing goes horizontally? If an object's not accelerating, what is the formula we use to determine how far something goes? Displacement is equal to what? Kale? Velocity is equal to distance over time, so distance is equal to, yes, velocity times time. VI times t, and what's t going to be? How long does the object move horizontally? When does it no longer move horizontally? Marina, what do you think? When it hits the ground. So the object, once it hits the ground, is going to stop moving horizontally, ideally. If that ground had not been a concrete floor, the bullet would have embedded itself in the grass or the dirt. So the time it takes the bullet to drop versus the time it takes the object to drop while it's moving horizontally are the same, and the time that it's actually moving horizontally is going to be the same here too. These guys are also equal. And so being able to break up a problem like this to say the horizontal and the vertical portions are totally independent of each other, the only relationship between the two is the time that we're going to allow these two things to interact, allows us to solve this problem to find the time that we're going to use over here. When you're ready, flip the page. Well, it's too late. I flipped the page already. Okay. Draw a horizontal line kind of from the dot over to the side. We're going to use the top and bottom half of your paper. I have to... You know what? This is really unfortunate timing.